Okay, so calculus 30, we're taking a look at differentiating the special e exponential functions with e as a base. And we know the wonderful part about this, e to the x, the derivative of e to the x is e to the x. That's amazing. So the case is also true, okay, dx of e to the u, right? It's e to the u times u prime, or derivative of u with respect to x. So even if we have some sort of function that's other than just x here, no problem. We just multiply by derivatives. So let's take a look at b first, okay? This is an important one because what you might not see is that this is a product rule situation. We have a definite x to the fourth type function and a definite e to the x type function. So that's product rule. We're going to have to do product rule there. So y prime equals. Now derivative of the first is 4x cubed times the second plus the first times the derivative of the second, which is just e to the x. So to factor, to simplify, probably a good idea to remove common factors, which we have an e to the x as a common factor. And looks like we have x cubed as well. So we'll take an x cubed out of there as well. And we have 4 plus x, right? So that's a little bit crowded there, but that's e to the power of x times x cubed times 4 plus x. So the other question we had here was about h. Okay, so let's take a look at h. So the derivative of this function, two ways you could express this before you take the derivative. You could show it as a quotient, which we see here, or you could show it as a product. And this would have to be to the negative 1. So whichever way you like to do it doesn't really matter. If you do it the product way and you bring this quantity up into the numerator and make a negative 1, their exponent, then product rule you might be more comfortable with. But at the end, you're going to have some things that have negative exponents on them. So you're going to have to bring them back down to the denominator anyways. So I don't know if it's any less work, but you might be more comfortable with product rule. So whatever you decide, one of these two. I'll just do quotient rule. So derivative of the top is e to the x times the bottom minus the top times the derivative of the bottom. Okay, so derivative of the bottom here is going to be negative e to the 2x. Okay, so the derivative of this is just itself. And we have to multiply, though, by the derivative of 2x. So that's going to be negative 2 e to the 2x, right? Does that look okay? All over the bottom squared. Okay, is everybody with me there? Does that look right, or do you have any issues with that? Derivative of the top times the bottom minus the top times the derivative of the bottom. So 0 minus e to the 2x times 2. Okay. So if we're going to simplify that, how could we simplify that? Well, I won't expand out the bottom. I'll just leave that for now. But it looks like I can factor an e to the x out of here for sure. And we'll try that. So e to the x, I'm left with 1 minus e to the 2x. And then looks like a plus 2 e to the 2x minus a negative there. And we have these e to the 2x's. I can combine those as well, looks like. So I'm thinking this is probably where we could stop. 1 and then minus e to the 2x plus, so that's plus e to the 2x. All over 1 minus e to the 2x squared. Might be a little bit tricky to see all that, but all right. So we have 1 plus e to the 2x. We have 1 minus e to the 2x. Those can't be simplified. Okay. Okay, so upon double checking, that is the answer for h. So if we zoom back out here, that's just a couple examples from question number 4. So anything else giving you guys problems there? Yeah? Number which, sorry? 8. Number 8? Okay. Okay, let me take a look at number 8. Okay, I'll give you a little hand with 8, but let's do number 6. Let's do number 6 first. Because this is implicit differentiation, and I'm just a little concerned that possibly that's a, come on now. So let's pull 6 into the notes here. Oh, actually I do have 6 right here. Okay. I'm ready for myself. Awesome. Okay, number 6. So we're taking the derivative of this, and again, you can't really isolate for y here. We can't write this explicitly because y is all caught up here in the exponent of the e function, and it's over here. So it's not reasonable to try and isolate the y. So let's just differentiate implicitly. Let's just take every term as it stands and differentiate each term, knowing that x is our preferred variable. So if we ever have to take the derivative of x, it's 1. If we ever have to take the derivative of y, it's dy dx, or y prime. And that's what we're going to try and solve for or isolate if we can at the end, okay? All right, so e to the xy. So of course this is an e exponential. So the derivative of this itself is simply e to the xy. But I have to consider that this is not just x. So I need to multiply by the derivative of this, right? Chain rule. Remember chain rule. This is actually a product of two separate functions. So I'm going to do product rule. So the derivative of xy is going to be the derivative of the first, which is just 1, times the second, plus the first times the derivative of the second. And I'm okay if you use the y prime there instead of dy dx. It's up to you. All right, so that is that's the left side. The right side, derivative of 2x is easy, that's 2. Derivative of y is easy, that's y prime. Okay, all right. All right, so what I want to try and do is I want to try and get the y primes together. Okay, so let's do that. This is going to be, what we have to do is we have to distribute this in, I guess. Let's distribute this in and see if we can get the y prime terms together at least on the same side so we can factor out a y prime. So this looks like e to the xy times y. You can put y wherever you want. I'll put it in the front there. Plus xy prime times e to the xy equals 2 plus y prime. So I have the y prime in these two terms right here and right here. So let's get those together on the same side of the equation. So I'm going to go xy prime e to the xy minus y prime. And on the right side, I'm going to have 2 and then minus y times e to the xy. Something like that. Okay. Now, if I look at just this part right here, I can pull out my y prime. See, y primes? I'm going to pull that out as a common factor. I'll change colors here so we can differentiate a bit between the two lines here. Differentiate. You like that pun? Maybe? No? Okay. Ex to the y minus 1 equals 2 minus exy. I've got exy right here. Okay, exy. Get that? It's like old English, like Shakespeare. Like Shakespeare. I know very little Shakespeare. What do I know? Nothing, actually. No, to be or not to be. That's Shakespeare, right? To be or not to be. I have ye xy over here. Come hither, fair Capulet something. I'm going to stick to math, I think, is what I'm going to do. I'm going to stick to math because decades have passed since I had to do anything really. Okay. Where was I? Oh, yeah. Final step. This is easy now. This is nice. Way better than Shakespeare, sorry to say. English teachers would disagree with me, but hey. We are going to simply divide by this now. That's multiplied by y prime. X e to the xy minus 1. And, put your brackets around there if you want. Okay. Shakespeare kind of messed me up here a little bit. I've lost track here, but I think everything's good here. Now, we can't divide any common thing out here. Can't factor, I think this is legit. Let's just take a quick peek. All right, so there's ye answer key. Ye right there. There's 6 right there. Okay, right there. There's the answer. All right, let's take a look at 8 then. 8 was the next one, I guess, that was mentioned before we get on to 8.3. Exciting. So let's do number 8 before we get into log functions. Doth glance from heaven to from earth to heaven as his imagination bodies forth. The forms of things unknown, the poet's pen turn them to shapes and give to airy nothing a local habitation and a name. Such tricks hath strong imagination that, if it would apprehend some joy, it comprehends some bigger than that joy. Oh, or in the night imagining some fear. How easy is a bush supposed to bear? There you go. That's some Shakespeare. I just remembered some. Good old Cole's notes got me through college. Woo! Okay. Where were we? Calculus. Did you guys like that? Did you guys like that? That was spirited reading, wasn't it? Wasn't that good? I have no idea what any of that meant, but hey, nothing's changed in 20 years. Okay. Now, number 8 is serious, though. This is not like Shakespeare. This is serious stuff. Okay? Shakespeare's a joke? I didn't say that. That's rude over there. Whoever said that. That's really rude. Okay? Find the intervals of increase and decrease for the function. So, may I remind you, ladies over there, thank you. I'll thank you to pay attention. Thank you. Usually the boys get in trouble, right? Hey, now the girls. Okay. Intervals of increase and decrease. Remember this from last chapter, from chapter 5 even. Take the derivative. No, you should remember this. Take the derivative. And then what? 0. Okay. Factor the derivative if you can. Do sign analysis. That one. So where the derivative is positive, that means the function is increasing. Where the derivative is negative, the function is decreasing. So let's give it a go. F prime of x. Oh, that's weird. Product rule again. Product rule. So the derivative of the first times the second plus the first times the derivative of the second, that's e to the negative x times negative 1. That's right. So I've got 2x over e to the x. I'm going to get rid of that negative there. Plus, or actually, let's just say minus because we've got a negative there. So minus x squared over e to the x. You see that? All right. I could have factored an e to the negative x out, which I will now. So 1 over e to the x times 2x minus x squared. I could get rid of an x in there too. X over e to the x. 2 minus x. Can I do any other factoring, do you think? You good with that? You guys good with that? Yeah? I could have taken an x and an e to the negative x out back up here, but I just did in two couple steps there. Okay, let's let this equal to 0. Nice. So I need to let each factor now equal 0 and solve for the x. So if this one, x over e to the x, if that equals 0, so what am I looking for? I'm just focused on the top here. Yeah, so x can't equal 0. If x equals anything else, we're good, but can't equal 0. So x cannot equal 0. Or that's the x equals, what am I saying? X equals 0. That is the 0. And then x equals what? 2? 2. Positive 2. So these are our critical numbers, right? So local max or mins will happen at these ones if they're going to happen. And is there anywhere where e to the power of x can equal 0, guys? Do we have an x that's associated with a critical number in the denominator down here? The answer is no, I don't think, because look at y to e to the x. Where does that equal 0? Nowhere. Doesn't touch 0. Right? No x value will make that 0. Okay? So e to the x will never be 0. No good. Okay. So this, I don't know why I drew that. That looks like a graph. It's not supposed to be a graph. It's just supposed to be one of those things. And the factors then are going to be x over e to the x, I guess, right? X over e to the x, and 2 minus x, and 2 minus x. Now you could split this up into x and 1 over e to the x if you like, which might be a little easier. I don't know. Let's do that. Let's make 3 factors. Okay. So x is positive. X is 0 at 0. Okay, we know that. Negative before that. Positive after that. E to the x. if we have to label something e to the x, I mean, we're talking about the y. So again, if we go back to that graph, right, what value for x makes e negative? Well, y is never, the graph is never negative, right? It's never below the x-axis, and it's never 0. So guess what? E to the x is positive all the time. Okay? Important to know. 2, we have a 0, and if we have a number like 0, 2 minus 0 is positive 2. So because we have a negative sign on that x there, this whole positive negative thing is flipped, right? Remember that little shortcut? Okay, so it's positive before and negative after. All right, so let's see. When we do all this, we're multiplying. So f prime of x down here is negative times a positive, so it looks like it's negative 0, positive 0, negative. Does that look about right? Now this is number 8, so some of you did number 8 in your homework there. So those of you that are, make sure you're double checking my work here for me. So what does this mean? Well, I have hello, what am I looking for? Tangent line, a slope of a tangent line. That was weird. See, Shakespeare messes me right up. So we've got a negative slope of a tangent line. We've got a 0 slope. We've got a positive slope. So that's a local what? Looks like a local min right there, right? And we've got a local max up here. So intervals of increase and decrease, well, we're decreasing. So decrease from negative infinity to 0. And then we're also decreasing from 2 to infinity. Does that look good? And increasing from 0 to 2. Okay, so does that check out? Let's just see. What is that, number 8? See if I can get to that solution manual again here. The solution manual that was created in 1969, I think, when they went to the moon. Something like that. Looks about, yeah, in the summer of 69, that's right. Some teacher made this answer key in the summer of 69. And you thought all this time it was a fun summer, according to that old song. Not really. People were doing math. Okay, so what do we got? Increase, 0 to decrease. Yeah, that looks right. Hey, we're good? All right. All right. So any other questions then about 8.2 homework here? I mean, if you were doing this last night, I know you were having fun, so it's good. All right, we're going to move to 8.3. Yippee. Hey, did I tell you guys yesterday you need to subscribe to my channel? I'm almost at 1,000 subscribers. Come on. Like and subscribe. Go to MrMathWell.com.